Okay, in this video, I'm going to solve a question on the rate of reaction. This is a question from May-June 2021 past exam paper. So it was question 5. Okay, let's see the question. Question 5. Two experiment 1 and 2 are conducted to investigate one of the factors that affect the rate of the reaction of aluminum carbonate. So this is the formula for aluminum carbonate. So the reaction is conducted with excess hydrochloric acid. So this is the formula for hydrochloric acid. The balanced equation for the reaction is this. You have it. It's given here. The apparatus used is shown below. So you have the apparatus there. You can see you have the aluminum carbonate in there reacting with hydrochloric acid. And you have the syringe. The syringe is collecting carbon dioxide gas, you can see. So you have your reactant on the left and your product on the right. The reactant on the left are used up to form the product on the right, or to produce the product on the right. So the reactant are used up and the product are produced or formed. Okay, now let's continue. The reaction conditions used for each experiment are as follows. So you have experiment number 1. You are given 100 cubic centimeter of 1.5 mole per cubic decimeter of hydrochloric acid reacting with 0.016 mole of aluminum carbonate granule at 25 degrees Celsius. And experiment number 2, you are given 50 cubic centimeter of 2 mole per cubic decimeter of hydrochloric acid reacting with 0.016 mole of aluminum carbonate granule at 25 degrees Celsius. So you are given aluminum carbonate in granule. You can see in both experiment 1 and 2, the aluminum carbonate is in granule at the same temperature. The number of the moles are the same, you can see. Only the volume and the concentration differs. Now let's answer the first question, 5.1. Define the term rate of reaction. 5.1. What is the rate of reaction? The rate of a reaction is the change in number of moles of reactant or product per unit time. So you can say the change in number of moles of reactant or product per unit time. Okay, so this is the definition of rate of reaction. There is also another definition you can give. So there is this one. The rate of reaction is the change in concentration of product or reactant per unit time. So the change in concentration of product or reactant per unit time. Okay, we can also give another definition. Let's say this one. The rate of reaction is the number of moles of product formed, or you can say the number of moles of reactant used per unit time. So you have 3 definitions so far, but the question is asking you to give only one definition. I believe it is good that I give you all these definitions so that you can choose which one works with you, and then you can give it whenever you are asked to give the definition of rate of reaction. And I also have a 4th one. The rate of reaction is also the volume of product formed or the volume of reactant used per unit time. This is the 4th definition. We can say the rate of reaction is the mass of product formed or the mass of reactant used per unit time. Okay, so you don't have to give all these 5 definitions. Just choose one definition. You can give the definition that works with you. So no need to give all these 5. Okay. Okay, now let's move on to the next question, 5.2. Okay, let me get the question. So this is the question. We're now doing 5.2. Okay, let me get it here. 5.2. Okay, 5.2. Using the experimental setup above, state the measurement that must be made to determine the rate of this reaction. So which measurement must be made in order to determine the rate of this reaction? You can see you have your apparatus there. Let me make it big so that you can see what is happening there. So you have the flask, and inside you have the aluminum carbonate granule, which is reacting with the hydrochloric acid. And then you have the syringe collecting what? You can see when you look at the equation, you can see you have carbon dioxide, the gas there. So when the reaction is proceeding, there is carbon dioxide being released, and the carbon dioxide is collected in the syringe there. So which measurement must be made in order to determine the rate of this reaction? We can measure the volume of carbon dioxide collected in the gas syringe per unit of time. So you measure the volume of carbon dioxide collected in the syringe per unit of time. Okay, that is one measure. Or we can say we can measure up the time taken for the aluminum carbonate to be used up. Because when you look at the question here, you can see when you read here, it says aluminum carbonate react with what? With excess hydrochloric acid. Hydrochloric acid is in excess. This hydrochloric acid, you have your hydrochloric acid there. So since the hydrochloric acid is in excess, this tells you that the other reactant is the limiting reactant. So you have two of them, this one and this one. If this one is in excess, the other one is the limiting reactant. So the amount of carbon dioxide produced or the amount of carbon dioxide formed will depend on the limiting reactant, which is the aluminum carbonate. Because when this finish, the reaction will stop because this is the limiting reactant. The hydrochloric acid is in excess. Okay, 5.2 will say measure the volume of carbon dioxide collected in the syringe per unit of time. And the other one can be, we can measure the time taken for the aluminum carbonate to be used up. So you can give either of them, this one or this one. So these are the measures we can take in order to determine the rate of reaction. Now 5.3, use the collision theory to explain how the average reaction rate in experiment 1 differs from the average reaction rate in experiment 2. When you look at the given information, you can see only the volume and the concentration differs. So 5.3, this is what I have. In experiment number 2, the increase in concentration of hydrochloric acid. You can see in experiment number 2, there is an increase in concentration of hydrochloric acid. So the increase in concentration of hydrochloric acid leads to what? More particles of hydrochloric acid per unit volume. And this leads to more effective collision per unit time. Okay, and this leads to higher rate of reaction. Okay, 5.4, let's get the question. The average, let me put it here. So the average rate of reaction in experiment number 2 during the first 2.5 minutes is 4.4 times 10 to the negative 3 mole per minute. So if you look at the balanced equation that you are given, you have your product on the right side and you have carbon dioxide gas, which is collected in the gas syringe. So the amount of carbon dioxide or the number of moles of carbon dioxide can be used to calculate the rate of reaction. But using the rate of reaction given, we can first find the number of moles of carbon dioxide after 2.5 minutes. So let's use the rate of reaction to find first the number of moles of carbon dioxide. So using carbon dioxide collected in the gas syringe, the rate of reaction is equal to change in mole over the change in time. And this is equal to the number of moles final minus the number of mole initial over time final minus time initial. I want to put this down a bit. Okay, we are going to find the number of moles of carbon dioxide collected in the syringe after 2.5 minutes because carbon dioxide is the product and it is used to determine the rate of reaction. And from there, we can now find the number of moles of aluminum carbonate. Okay, so the rate of reaction is given. You can see that it is 4.4 times 10 to the negative 3 mole per minute. Okay, 4.4 times 10 to the negative 3 mole per minute, which is equal to, so what is the number of moles final? It will be the number of moles final of carbon dioxide formed, and the initial is equal to 0. Remember, when the reaction starts, you don't have any product when the reaction starts. Do you understand that? When the reaction starts, at the beginning of the reaction, you don't have any product. So N initial will be equal to 0, and T final will be 2.5 minutes. T initial is 0. So this is what we have. Can you see N final? We are going to find it. N initial is 0. T final is 2.5 minutes. And T initial is 0. And now you can find the number of moles of carbon dioxide. So you have NF there because it's minus 0. And you have 2.5 minutes at the bottom because it is minus 0. Now you can use cross multiplication to find N final. So remember, this is over 1. So you have 1 times NF, which is NF. There is a 1 at the bottom there, and that 1 times NF, it will give you NF, which is equal to this times this. Can you see that? And this is equal to, let me close this. Now, what you need is your calculator to calculate this. Okay, I have my calculator there. Let's do it. Okay, so you have 4.4 times 10 to the power of negative 3 times 2.5. Can you see that? Which is equal to 0.011. Can you see? So you have 0.011 mole of carbon dioxide formed. Remember, why do I say formed? Because it is a product. Okay, now you know the number of moles of carbon dioxide formed in 2.5 minutes. Let's get the question again so that we can continue and see where we're going. So when you look at the balanced equations that you are given here, we calculated the number of moles of carbon dioxide formed. This is the carbon dioxide formed during 2.5 minutes. But we can find the number of moles used up of aluminum carbonate. So let's get the balanced equations first down. I'm going to put it in blue. Okay, let me remove this. So you can see this is the balanced equations there. Can you see it? Okay, let me put it here. Okay, this is the balanced equation that you are given. So from here, you are going to use the coefficient using your stoichiometry knowledge to find the number of moles used up for this amount of carbon dioxide to be formed. Let me say that again. From this balanced equation, you are going to use the coefficient there using your stoichiometry knowledge in order to find the number of aluminum carbonate used up for this number of moles of carbon dioxide to be formed. So this is your carbon dioxide on the right side as the product, and this is your aluminum carbonate on the left side, and this is the reactant. Okay, let's use the stoichiometry and the coefficient. Okay, so for 3 moles of carbon dioxide, can you see you have 3 there? 3 moles of carbon dioxide. This is equivalent to 1 mole of aluminum carbonate. Can you see that there is an invisible 1 there? So for 3 moles of carbon dioxide formed, 1 mole of aluminum carbonate is used up. So 0.011 mole of carbon dioxide is equivalent to what? We want to find the number of moles of aluminum carbonate in the 2.5 minute. Okay, so let's call it X. So we want to find X moles of aluminum carbonate. Okay, I hope you understand that. Can you see I've got my carbon dioxide on one side and my aluminum carbonate on the other side. This is what you should get first right. So now what you want to do is to solve for X. You are going to use cross multiplication. So you have 3 times X. You use your coefficient to solve for X. So you have 1 there, 3 there, 0.011 and X there. So let's use cross multiplication. So you have 3 times X. This is equal to this times the 1. So it gives you 0.011. Can you see that? 3 times X is 3X and 0.011 times 1, it gives you 0.011. And what is X? Let's solve for X. So to solve for X, we divide by 3 on both sides, by 3 there and by 3 there. When you divide by 3 there, you get the X. And X is equal to this divided by 3. Let's use our calculator again. So you have 0.011, we divide by 3. And this is what we have, 3.67. Let's round it off to 2 decimal places. So 3.67 times 10 to the negative 3. Okay. So this is what we have. Can you see from the calculator when you divide this by 3? Okay. So this is X. And this is now the number of moles of what? Aluminum carbonate used up. So when this number of moles of aluminum carbonate is used up, this number of moles of carbon dioxide is formed. Can you see? The reactant are used up to form what? The product. Okay, let me continue. Let me get a line here. Okay. Now to calculate the remaining moles of aluminum carbonate, remember the question is asking for the number of moles of aluminum carbonate remaining in the flask. Okay, you are going to take the total moles of aluminum carbonate minus the number of moles used up. So what is the total moles? When you look at the question, you can see you are given the number of moles at the beginning. Can you see? We are dealing with what? With experiment number 2. Can you see it's experiment number 2? When you go to experiment number 2, you started up with 0.016 mole. Can you see that? This is what you started up. And this is what is used up. Now you want to find what? The remaining. Okay. So you started with 0.016 mole. Okay. So the total is 0.016 mole minus the used up, which you calculated. So this is the used up. And this is equal to what? Let's use our calculator once again. Okay, so you have 0.016 minus this 3.67 times 10 to the power negative 3. Okay, so this is the answer. So this is the moles of aluminum carbonate remaining in the flask. Okay, so we have solved for question 5.4. Let's move on to the next question. I'm going to use the next slide. Now it's 5.5, I believe the last question. Let me get the question. Okay, this is our question. We are going to do 5.5, calculate the maximum volume of carbon dioxide that can be prepared at 25 degrees Celsius in experiment number 1. Take molar gas volume at 25 degrees Celsius as 24,000 cubic centimeter per mole. Can you see that? So we need to find what? The maximum volume of the carbon dioxide that can be prepared or that can be collected in the gas syringe. Do you understand that we can't use hydrochloric acid because it is in excess? We can't use it to determine the volume of the produced carbon dioxide. So we are going to use the limiting reactant in order to calculate the maximum volume of carbon dioxide collected in the syringe. And the limiting reactant is aluminum carbonate. So the production of carbon dioxide will be determined by the limiting reactant, which is aluminum carbonate, not the excess reactant. So you know from the formula sheet, which will be given together with the question paper, you'll find this formula. You have the number of moles is equal to the volume over the molar gas volume. So this is the molar gas volume. So you are going to make V the subject of the formula. So V is equal to this times this. So Vm is equal to this. You are given it. Can you see? We need the number of moles. We don't know the number of moles. Okay, we are going to find the number of moles. You can see the number of moles of what? Carbon dioxide, because the question is to calculate the maximum volume of carbon dioxide. And we are dealing with experiment number 1. When you look in experiment number 1, this is experiment number 1. This is your reactant and carbon dioxide is your product. You are given the total number of moles of this limiting reactant. So from the number of moles of the limiting reactant, you are going to find the number of moles of the carbon dioxide formed. Okay, so let's get the balanced equation down. Let me do this. Let me get it here in blue. So this is the balanced equation that you are given. Can you see? You are given this number of moles of aluminum carbonate. You want to find the number of moles of carbon dioxide. So you are going to use the coefficient there. There is an invisible one there, and you have 3 there. You are going to use stoichiometry to find the number of moles of carbon dioxide formed. So for 1 mole of aluminum carbonate used up, 3 moles of carbon dioxide is formed. Now you have 0.0, where is it? It's there. Now 0.016 mole of what? Aluminum carbonate will give you X moles of carbon dioxide. So we are going to find X, the number of moles formed. So you're gonna use cross multiplication. You have 1 times X, which is X, okay? And this is equal to this times 3. So it's 3 times 0.016, that is, and this is equal to 0.048 mole of carbon dioxide formed. So now you have the number of moles of carbon dioxide formed. Now let's get the volume. You have the formula there. V is equal to N, which is the number of moles. You have it there. So 0.048 mole times the molar gas volume. It's given. It was given in the question. So it's 24,000, this one. Okay. And what is V equal to? V is equal to, when you take this times this. Can you see the unit of volume will be cubic centimeter, because per mole and mole will cancel. Can you see this is per mole? So you have mole times per mole, it will cancel. And the unit will be cubic centimeter. Okay, let's get the answer. Let's use our calculator. So you have 0.048 times 24,000, and this is equal to this. You have 1152 cubic centimeter, or you can give it in cubic decimeter when you divide by 1000. So it will be 1.152 cubic decimeter. Okay, so this is the answer to 5.5. Okay, we are done with question 5 on rate of reaction from May-June 2021. If you haven't subscribed to your channel, don't forget to subscribe and activate the notification bell so that you can be notified every time I post new content for you. You can see down below is my name and the email address at which you can contact us. If you have any question or anything that you'd like to let us know, feel free to use the email address down below.